Thank you, friends, for thinking it's ridiculous as I think it is, but what can All right, and then just so you guys know, we have a quiz tomorrow, but I did put a review video up today just so that it helps review some concepts. So since this is going to be a bigger quiz, it's like 3 sections of the chapter. So, okay, let's obviously start with the first 3, which actually is more like the first 6 because part 1 or question 1 has like 4 parts. So I guess let's just start with question 1. Those are tough ones, and I'm not going to do all 4 parts, but I might do 2 of them if people need them. So what are you guys' thoughts here?
D.
D for sure?
Yeah.
I was confused the whole time.
So we'll do D first, which is a tough one, and then we can go back and talk about another one. So here's the thing, all right? I mean, this is where it's really helpful to like look at your book picture or the picture on there that I copied out of the book, because things look like this. I mean, I wish that I could give you some semblance of what this looks like, but this literally looks like something that has a circular bottom that has a pointy top, like is really what this looks like, because it's triangles everywhere is what they're saying. So how we're finding the volume is we are adding up all of the triangles and integrating them, because that would actually add them all up. But we basically just need to be able to say what the bounds are from here to here. So from here to here are the bounds. And then we basically just have to put in the formula for the area of the triangle. So here's what's nice for number 1, A, B, C, and D all have the same bounds, right? Because they're all the same circle on the bottom. So what are the bounds?
-1 to 1.
Perfect, because this circle, even though it looks like an oval with the way they had to draw it, this thing is a circle, okay? And it's a circle that's x squared plus y squared equals 1, right? So it's a circle that goes 1 in each way. So this is -1 and this is 1. And that's your bounds on each one. So if you're confused on all of number 1, every single part of number 1 has the same bounds, -1 to 1. So that's nice. Now, every single part of number 1, though, just has a different area formula, right? And then a dx. So that's the tough part about this one, is it says they're equilateral triangles. So we need to figure out what the area of an equilateral triangle is, but based on the fact, and here's the kicker, is this equation that I'm about to highlight in yellow, actually, because that might show it better. This equation right here is y equals root 1 minus x squared, right? Because it's like the circle equation, but getting y by itself. That is very helpful, because that actually lets you know, I'm running out of colors here, maybe I will use green right here. That lets you know that this radius in green is this. Usually whatever equation you have is like, in this case, it's not the radius of the circle. In this case, it's just that height from there to there. And that's going to be super, super helpful to know that this length right there is root 1 minus x squared. So this is where I'll go back to you guys though. What is the area of a triangle?
In terms of the diagonal, it's 1/2 d squared, right? I solved that on scratch paper somewhere. I don't know where I put the scratch paper.
It's square root 3/4 s cubed.
That might be closer. Here's what I would do. Let's start here first. Everybody, isn't the area of a triangle 1/2 base times height?
Yeah.
Right.
Oh,
Here's
what's
what's
the wrong one. My bad.
It's an equilateral triangle though. So like we actually can know what the height is related to the base. Now the base, we don't know exactly what it is, but we know that an equilateral triangle has what type of angles in it? Right? In the right
60 degree.
60 here and 60, and then this whole top thing's 60, so it could be 30. Is that okay for everybody?
Mm-hmm.
Now that's what makes this one way harder than A, B, C, or D. Okay, so once we go back and maybe look at A, B, or C, this one's going to be way harder than those, because those shapes are going to be way easier to find the area of. This one is just so hard because all of a sudden you're like, okay, I've got to try to figure out how to write the area of a triangle 1/2 base times height, when all that I know, And if you guys look here, all that we know is that this yellow thing right here is root 1 minus x squared. But what would that make the whole base of the triangle if I doubled that?
2 root 1 minus x squared.
Nice. So the base is actually 2 root 1 minus x squared because I just doubled the one length that I had, right? So the length that I had was that yellow piece and I doubled it. So that is the base. So now I've got 1/2, and then the base is 2 root 1 minus x squared. So that's actually kind of nice because the 2's are going to go away. Now I need the height. The height, since it's a 30, 60, 90 triangle, what's very interesting, if this whole thing is this, we actually already knew that half of it was this, right? It was 1 minus x squared. It's just this part, all right? But think of a 30, 60, 90 triangle. Isn't a 30, 60, 90 triangle like 1 root 3, 2 in that ratio, right? That means that like this side of it would also be 2 1 minus x squared because that's double of what that is. But that means that the height is just root 3 times root 1 minus x squared. So that is crazy.
Wait.
So height is actually root 3 times root 1 minus x squared. So, ew. That was gross. Okay, the A and B are much nicer than that, but that means that this is what goes in here. So I come back and I'm going to go -1 to 1 of root 3 times root 1 minus x squared times root 1 minus x squared. But everybody, what happens if you take root 1 minus x squared times root 1 minus x squared?
Square roots cancel.
Yeah, so I'm just going to take that out and just write it once. And I'm going to let you guys nint everything in this section. I think I mentioned that. This one is actually one of the nice ones that if I pull the root 3 out, I could actually do this one without nint pretty easily now that it's there. So I'd have x minus 1/3 x cubed from 1 to -1. I'm just going to have to multiply that by root 3 at the end. 1 minus 1/3 is 2/3, and then -1 plus 1/3 is 2/3, so 2/3 plus 2/3 is 4/3, 4 root 3 over 3. That's what I get as the final answer. Did anybody nint that and get that same decimal? I can type in 4 root 3 over 3 and see if that's what we get. But that was a nasty one. So really quick though, to help Eli out, if you're sitting there going like, this is really confusing, like what's going on? If I jump to a new page, like part A of number 1 is the exact same shape. It's just that there's circles everywhere coming out of this thing. And so that means that we still have just this, right? And we still have that height is root 1 minus x squared. But here's the beautiful part is the bounds are the same, we know, because they're going from here to here. And what's the area of a circle?
Pi radius squared.
Beautiful. So that's going to be the area of the circle. And then here's what's awesome is that this green thing right here that I've drawn in, isn't this the radius of one of these circles?
Yeah.
So boom, that's what goes in right there. And that one's way easier because it's just pi and then root 1 minus x squared. And the squareds go away and square root goes away. And so it's way easier when it's something that's not really hard, like a setup. So did anybody verify that there's a thing here?
No.
4 root 3 divided by 3. So that happens to be about 2.30 times. Is that what you guys got the nint? Anybody ninted?
Yeah, that's what I got.
Sweet. All right. What else did you guys want to do from, like, I could do one more. I'm not going to like finish, I'm not going to finish 1A here. I will let you guys go from there, but did you guys want to see the setup of either B or C? Or did you guys want to, yeah, go ahead. C? Yeah, we can see the setup of C. So C is now, I'm just going to draw a different, except for it's like squares whose this is what's tough. It says whose diagonals are on the line. So that means that this radius here is half the diagonal. So this is going to be crazy. So for C, same bounds, that's nice. But we need the area of a square. Now that seems easy, and it's actually way easier for part B because the side is actually on the bottom. Like if you see part B and C are both squares, but C is like a diagonal square. So how do we find the area of a square?
It's just the side length squared.
Yeah, it's just whatever the side is squared. Now here's actually, I'm going to tell you guys the answer to part B. If this was B for a second, then I'm going to go through and erase it. B should actually just have 2 times root 1 minus x squared in there, because the length of a side in part B is actually the whole bottom, which we said is double of that, length right there. But for part C, all right, that is not the case. All right. So how do we find, I know I've got way too many colors going on here, but how in the world do we find the side of, so if I'm going to just draw diagonal things, wow, my artistic ability just got really bad. I'm so sorry. So if all that we know is this, right, that's all we know, it's root 1 minus x squared, how in the world could we find a side length? Because technically this is a side. We need to take side times side.
Pythagorean theorem.
The diagonal is the side times the square root of 2.
Yeah,
And the
and actually either,
Add them together, I think.
yeah, either one of those methods will work. Like if we called this just S for side really quick, like we could do Eli's method of a side squared plus a side squared should equal double of this, because this whole thing would be 2 of those, this squared, right? So we could use the Pythagorean theorem, or I like Emma's idea. We could actually, I think it's going to be divide by root 2, but let's double check. So this would be 2s squared, and this side would be 4 times 1 minus x squared. And then we divide by 2, and then we'd square root. So s would equal root 2 root 1 minus x squared. Yeah. So this ends up being, I like both methods. That was good, both Emma and Eli. So you could use Pythagorean theorem with what you know, or you can use that. So that's what goes in here is root 2 root 1 minus x squared. Now that's just a side though, so I can actually square that. Woot. And so then it would just be negative 1 of 2 times 1 minus x squared dx. And this is what you would int on that one. Whew. Does that make sense to everybody? Those are tough. Hopefully that's helping a little bit. Do we need to do, just for sake of time, I'm not going to do both of them, but do we need to set up either part of 2 or 3? I would pick one of those, but maybe not both.
3, but I got B all right, but A was just causing a problem.
Are you guys good with 3A?
Sure.
Sure. Yeah.
All right, let's do it. So 3A, triangles again, coming out of this thing. So here's what's really interesting on this one, is in this case, we actually have the whole bottom, because we always, whatever function they give us, this function is 2 root sine x, whatever function they give us, that thing is always whatever height is depicted. So in this case, since this triangle doesn't go like this, right, it doesn't split the axis in half like the other ones did, this is right there, this is the whole base, right? And it does say equilateral triangles again. So this is where we're going to tackle that same thing, where we're going to have an equilateral triangle and it's 1/2 base times height, but we got to figure out what those are. So what are the bounds though?
0 to pi.
Nice, because that's what they tell us. They say, okay, from here to here, those are the bounds. And then we know we're doing equilateral triangles. We just need the area of the triangles, right? Dx. So all we know about this triangle is that the base is 2 root sine x. So that's nice. So we've got 1/2 times the base, which is 2 sine x. And then again from last time though, then how did we find the height? It's an equilateral triangle with like 60s in here and 30s.
It was √3/2 times the base.
Yeah, perfect. So it's just √3, like, so essentially like half of this would just be sine x. So it's √3 times root sine x. I like it. So this height is √3 times root sine x. Boom, so √3 times root sine x. And this is super nice. If you multiply all that together to put it in there, the 2's go away, the root sine x's become sine x, so you just get √3 sine x. I'm bringing the √3 out, so you could nint this again, but this one's just so easy. Let's do it. What's backwards from sine?
Negative cosine.
Nice. Negative cosine from 0 to pi. And isn't cosine of pi -1? Yeah.
Yeah. So it's
Negative
1.
it's minus cosine of 0 is 1, but it's -1. So you're going to have 2 times √3. So that's your final answer on 3A.
Huh.
I don't know where you got the √3 from still.
Oh yeah, let me go over that one more time. So coming back up to the top of this thing. So this is tricky, Eli, just because it goes back to geometry. So I'm gonna, instead of drawing the whole equilateral triangle for a second, I'm just gonna draw half of it, right? Because we know that the half that we're dealing with is a 30, 60, 90, right? Now, if the whole bottom though is 2 root sine x, then just half the bottom is root sine x. That's not what I meant to do. Is like this. Is that okay so far?
Yeah.
Okay. So then what I'm going to do though is I'm going to redraw 30, 60, 90, and we actually just have to remember from geometry, this is kind of gross, that regular 30, 60, 90 look like this, right? Kind of like regular 45, 45, 90s are like 1, 1, √2. And so then, like, technically what I'm doing is I'm doing a ratio in my head, but this is where I'd be like, oh, I want to know the height. So I'm going to say, okay, √3/1, because these are in ratio together, is equal to h over root sine x, because those are in ratio to each other. And we know that they're all 30, 60, 90, so they're equal. And then what I do is I just solve for h.
Okay.
So I both sides by root sine x, so then h would equal √3 times root sine x.
All right.
Will we
I
be
think
able
that-
to remember the sides of 30, 60, 90 angles and 40?
That is a great question. I'm pretty nice to you, and I stick with circles and squares.
Okay.
So
But
I don't think
also,
you won't
30,
use that.
60, 90 triangles and 45, 45, 90 triangles are in the unit circle
That's true.
with the
So that's,
hypotenuse of 1. So it's like a little bit different, but you can figure it out from there if you have to.
that's a good point. Good point. I like that. Yeah. All right. Those are tough. And just so you guys know, people have trouble with those every year. So if that was tough, then I mean that totally happens. Do you guys? We won't do both 4 and 5, but did anybody want one of those?
Yeah.
Which one does somebody want more?
Either one.
4.
4? Let's do it. Now here's where this may seem grosser than what we just did, because you might be like, we're revolving something around an axis, that's super hard. This is where I'm going to tell you guys, technically the rest of the assignment is easier, because the rest of the assignment is just circles. So it's either pi r squared, or you guys probably saw in the notes, sometimes there might be pi r squared minus pi r squared, because there's some sort of like hole chopped out of it. But in number 4, it says, here is this shape, here's 1. The formula is this, and it says revolve it around the y-axis. Now, everybody, here's why we needed y integration, was for this moment right here. Okay, so they're going to say revolve this around the y-axis. But as soon as you revolve something around an axis, it makes a circle. Everybody with me? So that's why these are actually just like super nice. So if I revolve this around, it would actually kind of make like a funnel shape. Everybody with me? That's hard to visualize, but yeah, that's like a funnel. So the question is, basically they want the volume of the funnel shape is really what they want. But the brilliance of this is that the entire rest of the assignment, we're not going to deal with triangles, we're not going to deal with squares, we're not going to deal with any of that. It's either going to be this scenario or this scenario. And everybody, which one is this? Is there like a hole in the middle of this funnel, or is this like a solid block?
Solid.
So, oh,
Yeah, so that means we're going to use an actual funnel would have a hole in it, so don't be alarmed. But this thing is just going to be like a solid block, and so it's just going to be the integral, and we got to find the bounds, and we got to find basically a radius that we're going to square, and then we're going to be done. Okay, so that's what we got to look like. So if we're y integration, though, this is where you got to be careful. This is where you got to look at it sideways, and you got to go from bottom to top, right? So what are my bounds?
0 to 1.
Beautiful. And then the radius is whatever comes off of the axis and goes to right here. But what do you guys think? That blue thing that I just drew, let me get rid of the other blue things that I have to not be confusing. Can we just use our function for that?
yeah.
Yeah. So if whenever we're going straight from an axis to wherever the function is, we literally just get to use our function for that. And it's already got x by itself. And so for y integration, that's perfect. So tan of pi over 4 y. And then you get to nint that, because if you didn't nint it, you'd have to do like substitution of trig identities and stuff. So I'm probably not gonna take the time to nint everything as we're going over homework questions. You guys can nint it, you'll at least know that I did that up right.
Ugh.
All right, which ones do we want to hit from? And these get a little bit trickier because you've got to actually like draw them or try to visualize them. So from 6 through 10, what do we want to do?
Ten.
Number 10. We can always do another one, so just because that's the last one is okay. So what's it say? Find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. So these are the two lines or curves, and it says about the x-axis. So if it says about the x-axis, what's nice is we know that we're going to use x integration, which is back to normal, not like that one we did. Y equals √2 is just a flat line at √2, right? So y equals √2 is somewhere in here. That's number 1. Secant. Doesn't secant look like this?
Yeah.
I think so.
Now what's interesting is they should have actually probably given you some bounds, because secant repeats itself and it's like down here and then it's up here. So it'd be like,
It was like in 3 different places.
yeah,
So
it would be infinite. So we could probably just use the one that's closest here. That's annoying that they didn't give you the bounds. Maybe they didn't give you the bounds because they wanted you to find these 2 spots where it crosses, because those are going to be our bounds. So that's a good question. How can we find those spots? So before we even talk about radius stuff, how can we find the bounds?
You have to figure out, like, set them equal to each other, so figure out where secant x equals √2.
Perfect. We basically use that substitution idea again. And I like that. You got to set secant x equal to √2 because those both equal y, and you can set it equal. And secant, doesn't secant equal √2 at like 45 degrees or the pi over 4s?
Yeah.
That's what I'm thinking. Yeah. So negative pi over 4 to pi over 4, because that's like the 45 triangles. So Boom. So our bounds are negative pi over 4 to pi over 4. So that's nice. All right, everybody. So here's a nice thing. Rest of the assignment, we're either doing pi r squared or pi big R squared minus pi little r squared. What type of situation is this if we start revolving this around the axis?
Second one.
Yeah, because essentially this thing down here is going to look like this. And if it revolves around, there's going to be a big hole in the middle, right? This is basically like an awkward looking ring because the outside would be flat, but the inside would like curve against each other. It would not be a very comfortable ring, but that's kind of what's going on. There's definitely an outside and inside. So this is going to be pi with some radius squared minus pi with some other radius squared dx. And our job is just to figure out what the two radii are. So the big R always has to be the one that goes to the outside. So that's from the axis all the way out to the outside. So what is this length?
Negative
Pi
2
over 2.
or root 2.
Root 2.
Yeah, positive just root 2 because it's actually, in this case, it is just root 2 the whole way. So you could actually be like, oh, that length is just root 2 everywhere. But it's because this is the function, right? And then in this case, that's just, since we're revolving around the axis, it's just whatever that function is. So it's there. And then what is the smaller radius?
Secant x.
Yeah, it's just whatever this thing is to the curve everywhere, but that's just that function. So it's just the secant x. And boom, actually this one, even though you could nint it, this one's actually super easy to do without nint. So that's kind of nice because you could pull the pi out of both, and root 2 squared is just 2 minus secant squared. And actually those are really easy to go backwards from because backwards from 2 is 2x. And backwards from secant squared should just be tan. And then it'd be from pi over 4 to negative pi over 4. And you have to multiply it by pi at the end. Here, should have 2 pi over 4 minus 1. And then you'd subtract out 2 times negative pi over 4. And then tan of negative pi over 4 is negative 1, so it'd be a plus 1. So then you'd have pi over 2 minus 1 plus pi over 2. You'd have pi minus 2 all times pi. Final answer, pi squared minus 2 pi. But if you ninted it, you just get that decimal of whatever that is. Nice. Should we do one more of 6 through 9 or jump to another one? What do you guys think?
Jump.
Keep going forward?
Yeah.
Anybody have 11 or 12?
12.
You guys good with 12?
12.
12. So it says about the y-axis again. So here we go, y integration. So what you got to be careful with that, like for number 12, if it says y-axis, and I'm going to graph these, they probably gave them to me in this form so I can graph them easier. But if we're doing y integration, should we have y be by itself?
No.
No, we should have x be by itself. So what should we do to that equation to get x by itself?
Solve for x.
Yeah. So x just equals,
Y squared.
yeah. And this one's just x equals y, which is obviously the exact same thing, but sometimes that helps. If I see y-axis, that's what I do a lot. And so now I just got to find bounds and what's going to be the outer radius and stuff. So I'm going to sketch this guy. I think they gave it to me in this form so I could draw my parabola, and then the line y equals x is just straight. So here's y equals root x, which we turned into, I should probably erase this into what we turned it into. We turned it into x equals y squared. So I'm going to make that one in black. And then this one is x equals y. So if this shape is going to go about the y-axis. So we're still in circles, obviously. So the main question is, are we doing just pi r squared, or are we doing pi r squared minus pi r squared?
Mine.
That one.
Second one. Yep, we got two radiuses. We got a hole in the middle. What do you guys think our bounds are?
Wherever the intersect is.
Yeah. Now this one is very nice. Be careful, because technically it's from 0 to 1, right? But shouldn't we be thinking this direction, not over this way, right? Technically, it's really nice because it's 0.00 and the 0.11, so it wouldn't matter. But think up and down technically. So bounds are from 0 to 1, and then what's the outer radius? So think from the axis this way.
The Y.
The curved one.
Just the line y equals x, so just the y. Nice. And then what's the inner radius?
Y squared.
Yeah, it's the other one, so it's y squared. So y squared. So this, what you're typing into int, is actually pi y squared minus pi y to the 4th. And again, that one's actually not that bad. And you remember, you can, for int, you can still use x's, then you can substitute. But that one wouldn't actually be one that's impossible either. It would just be gross. So that's what you'd type into int.
Why isn't it -1 to 1? Since it goes around all the way.
That is a good question. Basically, what's going on, I know this is kind of weird to, like, it's part of the visualizing thing, but since these are going around, what we're essentially doing is we're actually adding together a bunch of little, oh, that'd be the shell. What's a better way to explain this? Yeah, never mind. Hang on. Let me redraw that. It is kind of difficult, this one. What we're adding together is we're actually adding together a bunch of little washers. That's why I kind of said this was the washer method. So that washer is going to be smaller than this washer. And then this washer out here is going to be bigger. But essentially, this one little guy right here, just from these sections, since it gets swept all the way around, since it's kind of a washer in itself, it's actually already accounting for the other side.
Okay.
Yeah. It's basically based on that washer method. Whatever little radius is that you're calculating with, which we did, it accounts for the whole thing then when you sweep it around.
So what would happen if you did do -1 to 1?
You would get double your answer because you did it around twice. Yeah.
Would you in this case though, since it's like y, because there's nothing, or would it?
You would actually, in this case, you would get nothing because, well, actually, no, never mind. You would get double because technically, since it's y equals x squared, this thing's going down here.
Oh, so it's gonna be weird.
You would get really grossness because then you'd be doing. So Eli, you wouldn't get double. You'd just get like a whole bunch of extra crap. Because there's way more down there, like enclosed. So yeah, that'd be bad. What other one you guys want to do? I probably got time for one more.
13.
13. And everybody, I will tell you, I won't give you a word problem like number 14, but 14 actually wasn't that bad. You just have to do the integral from 0 to 6, and they give you the function already, and that's your radius. And it's not pi r squared minus pi r squared, it's just pi r squared. But 13 is a good one because of the different axis.
Mm-hmm.
So find the volume of a solid generated by revolving. Oh no, just bounded first. Okay, so y equals 2. Here's this line. It's in the first quadrant. That's helpful to know. Below by y equals 2 sine x. So this would be pi. So 2 sine x would look like this. It just has to, by pi over 2, it's got to get 2. It's got an amplitude of 2. On the interval from 0 to pi over 2. Oh, so it's nice. So it's saying it's bounded right here. So this is the thing we're looking at right here. And it says about the line y equals 2. That's where this guy gets confusing. So instead of going about the axis, right? If we went about the axis, we'd be doing this, right? We're actually going about the line y equals 2. So we're actually kind of going up with it, which is weird. It goes this way. right? So that actually changes things because the bounds are really easy, right? Either or. What would the bounds be on this thing?
0 to 2.
Actually, we're
Pi
going,
over 2.
yeah, we're going around
Oh.
thing that's parallel to the x-axis. So you actually have to use the x bounds, which would be from here to here. Yeah, so that is a good, I'm glad that we talked about this. Good. But then do you guys see here what's really interesting? If we were actually going about the axis, wouldn't we be using the pi r squared minus pi r squared method? Because we'd have a hole. But if we're going up around the thing up there, aren't we just going to use the pi r squared method?
Yep.
Because there's no, when you're going up around this thing, it's still parallel to the x-axis, but there's no hole. So we're actually using this method now because there's no hole in there. So it's pi something squared dx. So now we just have to find r. And that's the tricky part because the radius actually doesn't go from the axis to the function. Like if the radius was this, then the radius would just be sine 2x. It would just be whatever the function is. The radius actually goes from here. That's not what I wanted to do. Ah, come back. There we go. The radius goes from here to here. So how do I find that?
2 minus sine, or 2 sine x.
Yes, and if you guys are wondering like kind of what the visual of that is, that's because this whole radius, if we went down to the axis, is 2. And this tiny little radius right here is 2 sine x. But then if we subtract them, right, if we take 2 minus 2 sine x, that will get us what's in yellow, right? You got to take the big radius minus that tiny radius, and it gives you what's left over, which is what in yellow. So technically, this radius that we were looking for is 2 minus 2 sine x. And then you can int that. Husta, that is a tough section, especially visualizing wise.